Beneath New South Wales lies the fossilised remains of an ancient underwater metal factory. More than 430 million years ago, this was not dry land. It was the floor of an ancient ocean. Superheated fluids rose through volcanic rocks, erupted into seawater, and deposited copper, zinc, lead, silver, and gold around hydrothermal vents. Over time, sulphide mounds grew on the seafloor, while beneath them a hidden network of mineralised feeder channels carried metal-rich fluids through the volcanic rocks. Millions of years later, this fossilised vent system became the Woodlawn Mine, one of Australia's most remarkable volcanogenic massive sulphide deposits. It was not just a mine, it was an ancient seafloor hydrothermal system, folded, buried, preserved, discovered, mined, closed, and now being brought back into focus again. This is the story of the Woodlawn Mine. South of Goulburn in New South Wales lies a mine with one of the strangest origins in Australian geology. At first glance, Woodlawn looks like a base metal deposit. Copper, lead, zinc, silver and gold. A rich polymetallic ore body hidden within the rocks of the Lachlan Fold Belt. But the real story of Woodlawn begins long before mining, long before Australia existed in its modern form, and long before forests, dinosaurs or mammals appeared on Earth. To understand this deposit, we need to travel back more than 430 million years. During the Silurian period, southeastern Australia was not the landscape we see today. This region lay beneath an ancient ocean. Volcanic activity was taking place on and beneath the seafloor. Ash, volcanic debris, and fine sediments were accumulating in a marine basin. Beneath that seabed, magma provided heat. Seawater circulated downward through fractures and permeable volcanic rocks. As that seawater descended, it became hotter and chemically reactive. It began dissolving metals from the rocks around it. The fluid became a metal-rich hydrothermal solution. Eventually, those superheated fluids rose back toward the seafloor. When they erupted into cold seawater, the chemistry changed almost instantly. The dissolved metals could no longer stay dissolved. They precipitated as sulphide minerals: pyrite, chalcopyrite, sphalerite and galena. And within the broader mineral system, precious metals including silver and gold were also concentrated. This is the process that creates volcanogenic massive sulphide deposits, or VMS deposits. They are some of the most important metal deposits on Earth, and Woodlawn is one of Australia's classic examples. The simplest way to imagine it is this: Woodlawn began as a hydrothermal vent system on the floor of an ancient ocean. Hot metal-rich fluids rose through the volcanic pile. They vented onto the seabed. Sulphide-rich mounds accumulated around the vents. Beneath those mounds, the feeder system became mineralised as fluids moved through fractures and porous volcanic rocks. So Woodlawn was not simply a lump of ore sitting in the ground. It was an entire fossilised hydrothermal system, a seafloor vent field above, a stockwork feeder zone below, a natural metal factory operating on the ocean floor. Modern versions of these systems still exist today in the deep ocean, where hot fluids emerge from the seafloor and form sulphide-rich chimneys and mounds. But Woodlawn is the ancient version, preserved inside the rocks of New South Wales. The deposit contained two styles of mineralization. The first was polymetallic massive sulphide ore. This was the dense, metal-rich material formed largely from sulphides accumulating on or near the ancient seafloor. The second was stockwork copper mineralization. This formed beneath the seafloor, where hydrothermal fluids travelled through cracks and channels, depositing pyrite and chalcopyrite along the way. Together, these two ore styles tell the story of the complete system. The massive sulphides represent the seafloor accumulations. The stockwork copper zones represent the plumbing beneath them. This is what makes Woodlawn so fascinating. It does not just preserve the ore, it preserves the architecture of the system that made the ore. The massive sulphide lens was dominated by pyrite, with sphalerite, galena and chalcopyrite carrying much of the zinc, lead and copper. Silver was associated particularly with the lead-rich parts of the system, while gold occurred as a precious metal component within the polymetallic mineralization. Minor minerals included arsenopyrite, tetrahedrite tennantite, pyrrhotite, marcasite and electrum. That last mineral matters. Electrum is a natural alloy of gold and silver. Its presence reinforces that this was not only a copper zinc lead silver system. Gold was part of the Woodlawn story as well, and the grades were impressive. At the start of production, the massive sulphide ore contained approximately 1.7% copper, 5.5% lead, 14.4% zinc, and 89 grams per tonne of silver. The nearby stockwork copper ore averaged around 1.9% copper. These are rich numbers, and when combined with the scale of the deposit, they turned Woodlawn into one of the most important base and precious metal mines in southeastern Australia. But the ore body we see today is not preserved in its original shape. After the hydrothermal system formed, it was buried by sediments and volcanic material. Then tectonic forces began reshaping eastern Australia. The rocks were compressed, folded, faulted and metamorphosed. The Woodlawn massive sulphide body was folded into an open, asymmetric, west-plunging syncline. What began as a seafloor sulphide system became warped and deformed within the Lachlan Fold Belt. Yet despite that deformation, geologists can still read the original story. The alteration around the deposit is one of the key clues. Hydrothermal fluids changed the surrounding volcanic rocks over hundreds of meters. Primary feldspars and ferromagnesian minerals were largely destroyed. The rocks became chloritized, ceratized and silicified. Iron, magnesium, sulfur, silica and water were added. Calcium, sodium and strontium were depleted. These alteration zones form a fossil chemical halo around the ore body. They are the fingerprints of the ancient hydrothermal system. Close to the ore, chlorite and disseminated sulphides were most abundant. Further out, sericitic alteration became more widespread. Silicification extended even beyond the obvious phyllosilicate-rich alteration zones. To a geologist, this is not just altered rock. It is the frozen imprint of hot fluids moving through an ancient volcanic seafloor. The metal zoning tells the same story. Copper-rich mineralization appears strongly linked to the feeder system beneath the ancient mounds. Zinc and lead became concentrated in other parts of the system, especially where cooler, evolved fluids deposited sphalerite and galena. Silver accompanied parts of this polymetallic mineralization. Gold occurred as part of the broader precious metal suite, including in electrum. The result was a complex zoned ore system, built by fluids that changed temperature, chemistry and direction as the hydrothermal field evolved. This is why Woodlawn is so much more than a normal mine. It is a preserved cross-section through an ancient seafloor metal factory. The discovery of Woodlawn came much later. For hundreds of millions of years, the deposit sat hidden beneath the landscape. It was not found by someone spotting a giant outcrop of glittering ore. It was discovered through exploration. In the late 1960s, roadside soil geochemical sampling identified a metal anomaly. Geophysical surveys followed, including induced polarization work designed to detect sulphide-rich bodies beneath the surface. Drilling then proved what the soil and geophysics had suggested. A major ore body was hidden below. The Woodlawn Mine officially opened in December of 1978. The operation went on to process approximately 13.8 million tons of ore before closing in 1998. The mine produced hundreds of thousands of tons of copper, lead, and zinc, together with millions of ounces of silver and smaller quantities of gold. In modern dollar terms, the metals recovered from Woodlawn would be worth several billions of dollars, making it one of the most successful volcanogenic massive sulphide deposits ever mined in New South Wales. And that is the strange power of geology. A process that began as hot fluids erupting into seawater, eventually became a mine producing copper, zinc, lead, silver and gold from the Australian landscape. The mine later entered new chapters through redevelopment, resource reassessment and renewed interest in the remaining mineralization. But its geological origin remains the most extraordinary part of the story. Woodlawn is not just a big hole in the ground. It is not just a zinc mine or a copper, lead, silver deposit. It is the fossilized remains of an ancient volcanic seafloor, a place where hydrothermal fluids once carried metals through the crust, where sulphide mounds grew around vents in a vanished ocean, where copper, zinc, lead, silver and gold were concentrated by natural chemical reactions on and beneath the seabed. Today, Woodlawn stands as one of Australia's clearest examples of a volcanogenic massive sulphide system. The original mine may have closed in 1998, but the deposit still tells a much older story. Beneath New South Wales lies the preserved plumbing of a 430 million year old hydrothermal vent field, an ancient underwater metal factory, a fossilized seafloor system, and one of the most remarkable ore deposits in Australian geology. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.